I guess we're in class, and everybody seems to be there, most everybody, about 47 students. That's really great. So let me just do a couple of things in here. I got to get my sharing going. As you know, it's kind of critical for us to be able to get things going here. And I'm just going to get my iPad ready for, let's see if this actually makes me do what I need. All right. So let me just go ahead and do this. All right, now let's see. I want to get this out of here. And I want to do a sharing here, basically. All right, you're able to see my Zoom screen, obviously. There we go. And now we want to go to another class, not this one. That'll be ENEE350. As you can see, I got a lot of stuff in here. There's one of them here, right there. All right, I think this is where we're probably stopped last time, and I see that I use a lot of my color markers. There's only one marker, one pencil. I can select different colors on this. So if you just want to recall what we were doing, and then maybe there's a student or two that who may have just joined our class. We had this von Neumann architecture, if you remember, and in this architecture we had this very simple, loop, fetch, decode, execute, and then we had some 8 instructions to perform. And so the computer VESP 1.0 is what we introduced last time. We'll simply take these instructions from whatever program that we're pulling them, and then execute them. And once it fetches and decodes them, it'll just execute them one at a time. And whatever program we've written will then basically be computed or executed, meaning whatever that program wants us to do, or whatever we want that program to do, that will be done. So you can see that this is a computer program that's sort of executing over an algorithm, which can be a computer program in and of itself. And that was the principle which I used to actually create the simulator. So when we ultimately take a look at VESP 1.0 and all the subsequent editions of VESP 1.0, what we will see will be this program that's running underneath, which is then taking stuff out of the program that we want to execute, which is the program that we write in VESP. And so the VESP program gets executed over another program, which is this program that I created and I called VESP 1.0. And that was the exact idea of von Neumann. To him, a computer was nothing but a program. And so if somebody could go out and build that machine, whatever it may be, that machine will be then the program itself. And that will then execute the kinds of programs that we want to execute. So computers became no exception in terms of basically, crunching through programs. A computer can ultimately crunch through its own program. Of course, that will lead us to some fundamental questions in the theory of computer science and mathematics, whether a program will halt or not, the halting problem, so-called. And we're not going to get into those problems in this. We are actually very optimistic and positive about computers. We think that computers can do a lot of things for us, and they do, and there's no exception, I think. And we know the limitations of computers, but those limitations are no more or no less than limitations of human beings. Longevity, coherence, and all these other properties that humans possess or don't, depending upon the situation, are also attributable to computers themselves. So there's a lot of studies in that direction as well. But for us, I think it's important to understand the concepts, and also it's important to know, how to proceed with those concepts. Concepts are good, but they're not sufficient. Hands-on things will help us, especially in a class like this, to understand things from the grounds up, from bottom up. And that's why we're taking the time to do these things, in detail. Otherwise, we could sort of be very much at the top, and then, refer to these things as happening by themselves, not pay any attention to them, and then simply, assume that these things exist so we can use them, we can do things with them. Of course, that's not what
Sorry to interrupt, but there are people in the waiting room.
there are some people in the waiting room. Let's just go ahead and find who they are. There are two people, and they want to be admitted. And of course, there's really one person who wants to be admitted in two different ways, which we just did that. Okay. So now we are about a fifth as strong here, not counting myself, 49. Okay, so let's see, please remind me when that happens, because I don't pay attention to it much. I'm just simply focused on what I'm doing here. So so let's just, then follow things through as we did last time. Let me just go back to my iPad and then move on to the next place, and I'll tell you what we are supposed to do. We said that we'll take care of the move instruction in the next class, which we will actually do. And I showed you the execution of jump instructions are the easiest. All we have to do is just load the program counter with whatever address that our instruction contains. Remember, this was an instruction format that had addresses for these jump instructions. Like this is a force jump where we're actually supposed to go to a place in the program, and the place to which we have to jump is actually specified in this portion of the instruction register. And we do the same thing in the case of jump if zero instruction, except that we have to test to see if A is equal to 0. So this kind of gives us a capability to test something before we jump. Like in a higher level language, you can say if I is greater than 0, do this, that sort of thing, right? Even if the for loop or the other loops that you use in higher level languages, they have these boundaries where you have to test this. And that's how computers handle those loops. They actually have these kinds of instructions where they check to see if something became 0 or has been greater than 0, now becomes negative, etc. And then there is another instruction in here, which must be JPS. There are actually two more instructions. The JPS instruction, as you can see, will do the same thing, except that now we're going to test for A being greater than 0. That's the other condition that we have. Now the halt is the last of our 8 instructions. These are the last 4, as you notice: halt, JPS, JEZ, and then jump direct, that is force jump. Those are 4 of the 8. The first 4, if you remember, had mostly computational properties. Like first one was add, the next one was complement, and then we had a load and a move instruction. And I showed you how to load. Now I'm going to switch gears and I'm going to do the move instruction while we're actually building this, what we call the VESP engine. So the diagram that you have to picture to be able to understand this is something like this. You have to keep this diagram in mind. So let me just put another, I guess, lecture sort of separation in here. Okay. And this is going to be our lecture number 3. Actually, let me just do this on the next page so that I don't, I kind of start fresh here. Okay, so here's our lecture 3. So the picture that I think will be helpful to you in order to understand this what we were doing here is this. We have this thing called the controller. And we have this other thing called the data path. So here's our controller. And here's our data path. And our goal is to somehow perform these 8 instructions using our controller and the data path. So one of the very important things inside this controller is what we call an instruction register. Okay, the other thing that we have in here is the program counter. These are two very important things that sit right in the middle of the controller. Okay, that's our instruction register, which I abbreviate to IR. And this is our program counter. And in the data path, sort of indirectly, we have, this A and B register sort of setup, even though they are actually pointing to locations inside our main memory address space. We can sort of think of them as aliases, these things here, A and B, that sort of perform computations out of this ALU here. This is the ALU. In our case, our ALU is really simple. ALU sort of like decodes into arithmetic and logic unit, ALU, U for unit, L for logic, A for arithmetic. And we have this capability. We don't really have any logic per se in this case, but when we go to the 16 instruction edition of this machine, you will see that there is something called an AND or. There are two instructions that we actually add to the initial version of VESP so that we actually have proper logic instructions in it as well. But right now, we're limited to complement and add. Those are the only two things we have in this particular sort of setup. So suffices to say that there will have to be some interaction here, and usually commands will go this way, and then the flags will be up that way. So that's like a command. And this is a flag situation. Exceptions, like if you know how to program in Java, you probably know what exceptions are all about. Okay, you can throw lots of exceptions in Java, but here you have specific flags with which we actually specify how the ALU would let the controller know. Now there are really 4 flags here. Sorry, Joseph, who's asking? I'm sorry.
Is it like a if statement?
I cannot hear you. There's someone else that you want me to admit?
Oh no, I was just saying, is it like an if statement?
It's like no, it's not an if statement. It's like like you want to divide a number by 0, for example. Can you ever divide a number by 0, Jasser?
Nope. Nope.
So that will be an exception. Okay, that's sort of an exception it is. Now, flags will actually simply indicate what happens inside, what values that we get inside these registers. There's only A and B here, but we only check A. So there is this what's called a carry flag. What that tells you, it's not so much of an exception as it is like an indication of something happening. If something like a carry generates out of a computation, that means you have exceeded your representation. Right? You try to add, for example, let's just talk about decimal. If you add 50 to 51 and you only use 2 digits, you go to 101. There's no such number as 101. You're going to have to round it to like 1, mod 100. So carry must have been generated in there, which is our carry. What is our carry? In this case, that 1 in the 100. You got 2 digits. There's a 1 in here, but you don't see it because there's only 2 digits in your addition. Now, that's just an example, right? No matter how big a computer you design, you're going to have a certain number of bits. Today's machines are like 64 bits, which would correspond to some number of like, take the, I guess, 10 logarithm of it. You'll know how many decimal digits you're going to have in there. Probably 20, 1, maybe 22 digits. But that's the limit. You cannot go beyond that. Anything that you go beyond that, it's going to have to be notated as a carry. That's an exception. What? You understood it? I think your connection is a little tentative, so when you talk, I don't really hear what you're saying exactly. All right, so there's a carry flag. This will go up when the sum exceeds the representation's bit width, I call it. There's a 0 flag. If the thing gets to be 0, that is, if A becomes 0, this flag goes up. There is a sign flag. This means that if the number is negative, this will actually be 1. And there's what's called an overflow flag. And you learn this in your ENEE350 class. Overflow means that you add two positive numbers and you get a negative number. You all study two's complement representation. And if you add two negative numbers, you will actually get a positive number in case that you just go past the middle point. Like, for example, in 3-bit representation, you got numbers from 0 to 7. 4 on to 7 will be your -4, -3, -2, -1. And then the numbers from 0 up to 3 will be like your 0, 1, 2, 3. So if you try to add 3 to 2, you get a 5, but 5 is not a positive number in this representation. Rather, it's -3. So that's called an overflow. And you could similarly add two negative numbers, you can come up with a positive number. That's an overflow. Those are exceptions. Those are things that you want to know about, because if that happens, and then you make this assumption that you added some two positive numbers and you keep getting all these nice numbers that you think you do, but you're not, then the computer has to let you know that, hey, take a look at this overflow. Maybe you want to do something about it. Usually these are passive exceptions. In other words, it's up to the user to figure out exactly what to do with these. Now, if they were to be active, you would probably get a real hard exception where you won't be able to do much after that. That means your computer will go into some strange behavior. Let me turn on the lights here because I think the light is coming from behind here, and therefore you may not be able to see not that you're probably interested in my image as much as you're interested in the iPad image that I'm reflecting here, but just in case. Just a bit of light is coming from this side. Hopefully that will just make it a little easier for you to see me here. All right, maybe a little better. All right, Yekta, you're okay? You're good to go?
Well, what do you mean?
Are you okay? Are you following the class?
Yeah.
Good. I appreciate that. Just wanted to check. And I can only see you live here. I think everybody else is like hibernating somewhere. And I see Jasser now. All of a sudden he popped. Good to see you guys. It's good to have, I guess, breathe some life into these lectures that are so remote and almost non-existent in some sense. Okay. All right. Now, so let's get back to work. After all this stuff. So the controller is critical. The data path is critical. And what we're going to do today, we're going to write draw some hardware circuit, some sequential circuit, which will actually capture what the controller does. Okay. So we're going to borrow some ideas from your ENEE350 background. And that background should help you understand what the controller is supposed to do. And this controller that we create here in terms of flip-flops and other things have also been pushed into a program which is called VESP 1.0. I'll take a look at that if time permits today, if not on Thursday. And we're going to write some programs on it. So let's go and then take a look at the controller. So let's see how we're going to do the controller. Okay. So we will now construct the controller. Sometimes we call it a sequencer for VESP 1.0. Now, again, as I've been saying to you before, as I said to you before, we can take a very complex machine and then implement that instead. I can give you a controller for a 300 instruction machine, but it'll take me maybe all the time through the semester to explain all of those things to you. And I think we'll waste a lot of time that way. So the reason that I picked this very simple architecture is because I can actually wrap it up quickly. There are only 8 instructions. All I have to do is explain to you what happens with those 8 instructions. Now, remember, we had this sort of conceptual diagram: fetch, decode, execute. This is what we're going to do. And we'll repeat this forever. That's what computers do. When you turn them on, that's what they get into this fetch, decode, execute process. So we're going to have to do each and every one of these steps as we build this machine VES 1.0. So we're going to make an assumption or two, and the assumption is this. We assume that D flip-flops are available. And we use a synchronous logic, meaning that we have a clock. So those are our assumptions. Let me show you what a D flip-flop will look like in our sort of context. And then I'll use those D flip-flops to do what we have to do, okay? By the way, some of you asked me about these classes where they are recorded. Now, I just figured out finally that University of Maryland cut a deal with, I think, Panopto, whatever. And now most of our classes are actually posted there, their videos. In the past, I would simply say, store to the cloud, and the thing will go to Zoom somewhere, and then you will actually get it out of there. Now, this time, I clicked on a couple of my, Zoom keeps sending me messages saying that, your recording is now available or something. When I clicked on those links, I went to nowhere. So University of Maryland made a sort of a deal with, I guess, Panopto to have those things recorded over there. Now, I was required to actually link somehow the Zoom videos to that place. It seemed that way, at least our IT people told me that that's what needs to be done. And unfortunately, on Zoom, there is a one of those things that you can actually move around. That's called Zoom captioning. Now, that's not what I apparently was supposed to do. There's also something called Zoom recordings as an option that I can, as an instructor on my side of Elms, I can move that and make it visible. It turned out that that thing was not visible, could not be made visible because the system administrators locked that up. So I tried a few times, and then finally I was able to communicate it to the IT people, and they kind of fixed it. And I think if you log into Panopto, you should be able to see my lectures without any problem, okay? So that's just, and I promise to have you see them on Zoom Cloud. That's not gonna happen. I assume that it was a little too expensive, I think, for the University of Maryland to get all these classes recorded, because we all just clicked on that, record to cloud business. And I think it piled up, and the University of Maryland found it a little too expensive to handle it. And now they're pushing it to Panopto. But that integration was partially left to the instructors, which I thought was not a good thing, because why should I bother make this integration myself? I mean, I'm just teaching a class here. I'm not a system administrator or an IT person. And then not only that, but they locked it up so that I couldn't even do it. And that's a lot. I'm sure that some other professors maybe, you guys may find your way around so much easier, a lot easier than I could. But anyway, they're out there on Panopto, and I hope that you're able to see it. All right, now let's get back to class. So, these are two things that I'm going to do. When I write draw a flip-flop like this, let me just do this. I think, when I do this, I should really be using this. Even that didn't work. I just have to get a little better, a little I have to improve myself here. There you go. I finally got it right. So now let's just draw something here. Draw something there. Call this D. Call this Q. And then call this clock. So this is our D flip-flop. You know, all that does is whatever appears on the D input gets to be there on the Q output a clock cycle later, okay? So it's really sort of like a delay. That's why they call it a D flip-flop. You get to see whatever D is a clock cycle later on Q. Just the separation by a clock cycle in time is all there's to it. Now, the way we're going to use it is we're going to draw a little arrow this way. Okay. And this arrow will really indicate that we're doing something with this particular, what happened there. That arrow is sort of like going to tell us when we get there. In other words, when there is a pulse at that Q output, something will happen. Whatever will happen, I'll write at the tip of that arrow. Okay. Whatever action that my sequencer take will actually be written up there. And so we have three things to do: fetch, decode, execute. And then, for example, I have to write something in there for fetch. And the very first thing that, if you remember, that I did when I was trying to, you know, when I talked about like fetching an instruction, maybe I didn't talk about it explicitly, would be to copy the program counter. Remember now, remember that the PC points to the next instruction. What that means is that I'm going to use that property of the PC to actually grab an instruction. So that flip-flop representation is going to be used now to create the fetch process. So in order to do the fetch with these flip-flops, here's what I need to do. Okay. So the fetch process is going to look like this. I will have this flip-flop, which I will call my flip-flop number. Wait a minute. I just realized that I was not doing what I said I will do.
So, Professor.
Yes.
Would it write fetch on the, like, you said it will write whatever we are doing, the process on the.
Yes, here.
Yes, so it would write fetch, decode, or execute, or it would write.
Well, in a sort of a macro way, yes, they will say fetch, decode, execute. In fact, I could just, but you know, fetch has to have a hardware sort of implication. You know, it's not like if I just say fetch, I mean, who will understand that, right? So we have to put it all in the context of the registers that we created. If you remember, we had an MAR, MDR, PC, IR, A and B. Those are our registers. Whatever we do, we have to do them in terms of those. So if I just said fetch, it'll be a little ambiguous as to what I really want to do. I'm basically writing the sequences so I can make it extremely precise, so that that fetch thing that we have in mind is going to materialize somehow on a piece of hardware. And our hardware has these things that I just mentioned to you, among other things, right?
So that's fetch, inside of fetch, we have like a couple of those.
Yes, you will just see that in momentarily, because I'm actually starting to draw that now.
Okay, thank you.
Yeah. So this is our very first flip-flop. Let me just move it up here a little bit. I can't do it apparently, but actually I can. Yeah, there we go. So in this fetch, we have a D input, and we have an output. Okay, let me just draw this a little shorter. Okay, and let's call this flip-flop maybe 1. Okay, And so there is this D1 input, and then there's this Q1 output here. Actually, let me write this inside, just like I wrote it there. Okay, that's my flip-flop. And I'm going to draw an arrow here. So that arrow is now going to tell me what I should do to actually fetch an instruction. So the very first thing that I have to do when I fetch an instruction is to move the program counter into the MAR, because my instructions are part of a program that I originally stored in my computer's memory. Okay, so I'm going to have to say here, MAR is equal to PC. Now that I've done this, I also would like to write right underneath this another sort of like step that has to be done concurrently to this. And that's going to be like PC is equal to PC plus 1. Because I know that if I ever come back to this place later in the program, later in the loop, the fetch, decode, execute, I don't want to end up fetching the same instruction again. So since I could do this anytime after this, or about the same time I'm doing this, I just want to make sure that I actually get to do that, and those things get done as early as possible. There's no reason for me to wait for that, because I'm not going to use that for a little while. Until I get a load or a move instruction, you'll see that'll be very useful then. So now that I've done that, I will just move on to the next place, right? So that I've done this thing.
Professor?
Yes.
Quick question. So,
Gabe, I'm sorry, Gabe, yeah.
no worries. So when we're setting MAR to the PC, that's after the PC has already seen like the load or move instruction, and then it's moved down one to the address, correct?
Yeah, so we're assuming initially that, when you start writing, executing a program, there is some global thing that it's going to initialize this PC to where the program is, stored at, like the very first instruction in there. So at the very beginning, PC is initialized. We're not interested. We're looking at the steady state. PC would have been initialized before we get to execute this program.
Right, but for example, the
Yeah.
load and move instructions, after it sees that like the instruction says to load or
We will
move,
increment it one more time.
and then you set the MAR to it, correct?
Right. Not yet, though. We're not doing one of those two instructions that you're referring to. So, we assume that we may not do them, for example. But when we get to those two instructions, their execution, we got to get this PC incremented one more time.
Okay, I understand. Thank you.
Yeah, we will do that, absolutely. But right now, we're not concerned because we don't even know what instruction is coming down the pipe.
Okay.
Thank you, Gabe. All right, so now we've done this. I'm going to, go to the next place. So I just pushed the program counter, which is pointing to the next instruction in the memory, into MAR so I can read it. So I'm going to go ahead and do that. I need another, flip-flop for this. Okay, here's my next flip-flop. And I'm going to take that flip-flop. I will call this D2, Q2, and it'll be flip-flop number 2. And at the output of this, I might have to do something. And that thing will be, again, something that will just sequencer, must help me with. And now that the MAR has the address of my sort of next instruction, I would attempt to read it into MDR. So I will simply say this, MDR, sorry about this. I'll write it a little bit to the left. MDR equals MEM, just abbreviated, MAR. Okay. And then I want to do something called read equals 1. That means like I want to read something. And I want to do these things all at the same time, kind of. So now I know, when a pulse kind of like goes by this flip-flop, I know that I've copied my memory into MDR. So my MDR now contains my instruction, but I want to have it in a different place than MDR. I want to move that now into another place, which we call the instruction register. That's where it's going to go. So I'm going to go, from here. Let me call this point maybe, like B or A, maybe. Why do I call it B? I'll start now with A. Like A is on my left-hand side here, okay? So here I am. Okay. And I will have this A come in from there. This is like A, point A. Okay. Because I'm out of space, I just have to draw it on the next line. I don't have any space on the right-hand side, so that's why I moved it down here. Okay, so here's D3.
Professor.
Yeah.
So in this case, the way you draw it, Q1 does not equal to D2? Or it does?
I mean, there's a wire, so they are the same.
So Q2 equals to D3?
Yeah.
Because I thought since we are having that flash and like there's a little process in the middle, I thought maybe not, but does that?
If I had space on this, I guess paper that you see, so to speak, if it just extended itself this way a little bit more, I wouldn't separate.
I understand that. So whatever it's happening, like MAR equals PC, is that happening inside the flip-flop?
No. These are commands that are going to the data path.
Okay.
These arrows, that's why I use arrows. They go to a place. This is where they're going to go. Remember this diagram? I said it'll be helpful if actually you keep this in mind. Commands. You see the commands? You see it there? Now those arrows are the commands. They are generated by the controller. They're going into the data path.
For this
is
example,
all about timing. This is all about timing. We're trying to time things. Yes, Michael.
so for this example, all those data points that are getting sent in are going to be the same, just delayed by 1. So why wouldn't you just set up like a delay and send the same bit, like the 0 or the 1, like delayed to each like register, or like whatever these lines are going to.
So finite state. You learned about finite state machines in ENEE350, correct?
Right.
So we created these sequential circuits, yes?
Yeah.
So sequential circuits use flip-flops in order to separate states from each other.
Okay.
And D is a flip-flop. So we have flip-flops separating states from each other. Each flip-flop sort of stands for something, which is like a state.
Okay, yeah, I remember that now.
Okay, thank you. Yeah, that's, it's important. Like, we take these classes, they really come back and then help us understand these things, like, because we couldn't put 244 and 350 into one class. It just take too much time to cover it in a semester. That's why it's really important that we require these things. And I'm sure that you learn it quite well. Okay, so let's just not, stop here. Let's just finish this fetch. So what do I do next now that, I get to be here? Okay. This is my next place, and where's the ultimate place that I have to push this so-called instruction that is sitting right here squarely in MDR. You see that right there. It's in MDR here. I have to push it to where? I have to push it into its final destination, where IR executed, right? So here's the next step then. IR is equal to MDR. So when I get to that flip-flops output, let's say that I push the pulse in here, okay? and a pulse appeared here. And then that pulse disappeared. When this pulse appears, this pulse disappears. Disappears, appears. Disappears, appears. Do you get the idea? This pulses are going around, the system. Wherever the pulse is what we do. It appears. So when the pulse appears there, we know that we actually have requested. We have requested that MDR be copied in IR. When will that copy be completed? When we get past another flip-flop, because that is where the request is made. This is a request that is being basically created. Request is made. Request is made to copy MDR into IR. Now, we cannot process the bits in IR for decoding until we wait a clock cycle. Okay. So we this arrow simply says move MDR into IR. It hasn't moved it yet. We got to wait for a clock cycle for that MDR to mature into IR. We cannot just simply, start doing something in there, like decode the instruction. I cannot just dump a decoder in front of that. I got to wait a clock cycle so that my bits, the bits in my IR actually are firmly established. So let me just say that we need a clock cycle for our instruction to settle into IR. So we just have to take another, I'll call this point B. Okay, that's point B. I'm going to move from there to another flip-flop. I'll just copy that arrow in there so that I'm replicating this information as we go forward. Everything is clear up until now, everybody, right? It looks like everything is okay. So let's move down a little bit. So now I'm at point B, okay? I'll just copy this IR equals MDR so we know what we're doing there. But this completes the fetch process. Let me write this also. These three flip-flops plus the next one complete the fetch process. Okay, now let's go ahead and then basically start with point B. So here I am at point B. Okay, and this I call D3. Q3, and this is our flip-flop. By the way, this was flip-flop number 3. And now this is our flip-flop number 4. Okay. And we head over here. If you look, IR equals MDR. We said that hasn't happened yet. It will happen once we get past this, this flip-flop over to the other side. Okay. So now here I am. And at this point in time, I have my so-called instruction already matured into IR, okay? I'm not going to write something on this yet, because, you know, I will tell you what happens before I go proceed with this. So now that I'm here at this point, we can call it, you know, C if you like. Maybe I can just call it point C. That's not right.
Professor,
Oh, yeah?
aren't they supposed to be D4 and Q4?
Yes, they are. I'm sorry. I apologize. Yeah, I don't know how I did that. Sometimes I say one thing and I do another. Thank you for that correction, Hector. Okay. All right, now. Again, in ENEE350, you learned about a great combinational circuit. That circuit is going to be very, very helpful in this sort of situation to us. Let me just say this here. You know, execution can begin, decode and execution. And what kind of a circuit will that have to be then? Right? I mean, the word is there, decode. So we have to use that decoder. So what we do, we take a big decoder. How many instructions do we have? You all know this by now, right? We have a total of 8 instructions. VESP 1.0 has 8 instructions. So we're going to put now those 8 instructions in front of us. Here's how we do it. Here's our decoder. Okay. That's our decoder. And this decoder has to decode 3 bits of opcode into some 8 outputs. So this is actually a 3 by 8 decoder. Okay. It's got 3 inputs. And what do you think those inputs will be? Okay. So what are these bits? These are the bits of our instructions, the leftmost 3 bits of our instruction registers, right? Register content. So here's IR0. IR1. IR2. And we get these from where again? We get them from the instruction register. That's why we brought them into that place in the first place, right? I just said decode and execution can begin here because our instruction holds our instruction now, our instruction register. So there are some 8 outputs here. One of them will be, the first one will be, let me just do it this way. This one would be an add instruction. In other words, if that wire is hot, that is, it's equal to 1, then we know that we're doing an add instruction. So that's like an add. Okay, I just take it as add. The next one will be, as you know, the load instruction. I'll call this like, you know, LDA. The one after, and how do I know these things? I just look at them, look at these bits, IR, I0, IR1, IR2. And if they're all 0, that means add is hot. If they are 0, 0, 1, that's not load, by the way, it's complement. I take it, I just realized that I wasn't doing it. Here we go. Complement. Okay, CMP. The instruction after that is load. LDA. The instruction after that is move. The instruction after that is jump. Instruction after that is jump if 0. Instruction after that is jump if positive. And the instruction, the last instruction we have is halt. So those wires will be hot depending upon what 3 bits I feed into this particular system of decoder, 3x8 decoder. Now we have this wire here, which is kind of waiting to work for us. We take this wire. Sorry about that. We take this wire. And then we end it with this wire. Like so. And we call this add. Basically, this is like the add command that runs into add command.
So is this like an AND gate?
It's an AND gate. It doesn't look like one?
Yeah, just making sure.
Okay. No, it may not. I'm just, because my drawing is not perfect there. Yeah. So that's an AND gate, which now combines 2 things. That our sequencer tells us that we actually happen to be here. This is, by the way, this was point B, which I have to write here. Okay. Yeah, this, of course, is one a plus. There's a minus sign to this nice capability here. Okay. Now we take that same wire here, and we bring it up here with the complement. Put another AND gate on this. And this is our complement command. Okay, so you get the idea. Those things have been done with right away. So we don't really have a lot of work to do here, because add is, as you learned in, again, ENEE350, it's a combinational circuit. Remember that ripple adder or a carrier look-ahead adder? They were nothing but a bunch of gates put together, right? So we have no sequentiality per se when we think about those things.
Professor,
Yeah.
Does this go like you have AND gates with every single one of the decoder output with Q4?
Well, not all of them will have, like that C will have to be ended with every one of them. That is true, but we have more work to do when it comes to these other instructions. Whereas that add instruction, add command, which is, you know, on the output side of that AND gate at the top, that's like a wire that's going to go into the A register's D input. The inputs are flip-flops in a register, as you know. Every one of them will receive this as an input, so that once we add these two numbers, A and B, let's say, then the result will go into each and every flip-flop to represent the sum. So that's like a gating sort of process. We try to gate A, the register A, with some number, which is the sum of A and B in that case. And just like all the other registers, A is a register. If you just look back here, always keep this in mind, right? A is a register. It's got a bunch of flip-flops in it. That's how we made registers in ENEE350, if you remember. They have some flip-flops in them. Each and every flip-flop will have to be excited to get whatever the sum is. And we're going to put the ALU will have this, either the ripple adder or the carry look-ahead adder, other adders, etc. Whatever adder you choose to use, that's going to compute the sum of A and B and push it back into that A register, bit by bit. Of course, in parallel. We're not going to take, 16 clock cycles to do it. It's not a sequential or serial adder.
Okay. And you know how we had fetch and then we had decoder and execute. So the first three flip-flops that we drew, does that is that fetch? Like fetch takes three flip-flops?
Yeah, the first three, flip-flops just completed, as you just see, IR equals MDR. But then I said, like plus the next one, which is basically we put in here, right? This one right there, D4Q4. That is what is making it available in IR. Before then, we made a request to get the MDR into IR. At the end of that clock cycle, D4 pushed itself through the flip-flop and now appeared in IR. When the clock happened, MDR went into IR, not before that.
Okay. And we are in the decoder 3x8 is the decoder part, and we haven't got to execute yet.
You're choked a little bit when you talk. I don't know why it is. Your phone may not be right. What is the question?
I'm saying that have we not reached the execution part, or the 3x8?
Yeah, when we get to see, we are in the decode and execution. As it says, decode and execution can begin here.
Oh, both of them are okay.
It
Okay,
says
thank
it can begin here, and
Okay.
we just began doing that. Yeah. So now let's go and take a look at yeah. Let's go ahead and take a look at I don't know. I don't want to touch this thing. So how do we do the LDA? Let's go ahead and take a look at LDA. Now let's first of all picture this LDA in our thoughts again. And remember, we incremented the program counter in here, right there, at the end of the first, clock cycle, right there. So we know that if our instruction were to be a load instruction, our PC would have looked at the right place because we incremented it to look at the second 16 bits of our instruction. These instructions, LDA and move, have two consecutive 16-bit pad, values. Our first 16-bit was like 3-bit of opcode plus some address. And then the bottom 16 bits was our operand in this case. So what I'd like to do is to move that operand from the memory into the MDR so I can actually put it into wherever it's supposed to go, which is in the first, and not the first, in the last 13 bits of my IR, the address. Okay, so let's just, visualize this. Okay, I'm just going to draw something here so that I can write something there. Okay, so here's how a load instruction kind of looks like. There's an address here and there's the data operand. And at this point in time, our PC is actually looking right there. That's where the PC is pointing to. And this is the destination address. And this is the so-called LDA instruction inside the memory. Okay. So now we know that our so-called address to access the operand is sitting in PC, okay? And I could have benefited from copying this PC into MAR so that I could actually save myself a clock cycle. What that means is, while I'm actually copying here IR into MDR, I might have as well copied PC into MAR. Not that I'm going to do a load instruction, but you notice that the add or the complement, that the first two instructions will certainly not be impacted from my moving this so-called address that sits in PC into MAR. That would have no side effect. If I actually end up doing this in step B, that is where that B is pointing to, rather than wait until I get to C and then I actually but I copy PC into MAR. That would have meant I had to wait for another clock cycle to be able to take that LDA wire out of there and then hook it up with, the output of that next flip-flop and then perform my computation. Instead of doing that, and to make the long story short, I'm just going to add one more thing in here, which will be just like this. Let me just bring it down here. I will simply say MAR is equal to PC also. Two things get done here. One is this, and the other one is this. Okay, now why did I copy PC into MAR in there rather than wait for a clock cycle to do it? Because if I did it there, I don't now have to wait for another clock cycle. I don't have to insert another clock cycle when this LDA thing happens, so that I will have, one more clock cycle in the end. So if I had actually done that copying here, that means when I get to be here, in other words, now let's just pick up the same wire from here. And then, basically connect it to this LDA. Okay. So that means I have already copied PC into MAR, and all I have to do at this point in time is to perform my reading. What am I going to read? I'm going to read what is in that operand section in the second 16 bits of my instruction and push it into MDR, okay? Now that is just simply going to extract it from there, but I also have to put it back into the place which I call the address. So let me see, I don't think I can fit everything in here, so I'm going to give this place a name. I will call this place D. So I'm just, splitting into little bits and pieces so you follow this. All right, so now let's go ahead and do D. What time is it? Actually, my power is down to 15%. I don't want to lose the class. Let me just actually power myself up a little bit, put something here. go. All right, so now we have this thing here. We are at point D now, okay? At which time we know that we have, so I'm going to put this as flip-flop number 5. And we are at point D. Okay. This is flip-flop number 5. This is D5, this is Q5, and this is my point D. Okay. And at that point in time, I can actually do this. Let me just do one quick surgery. Okay. And here, I want to start doing something. I happen to be there, and I am just going to say this. MDR. Sorry about that. Is equal to MEM, MAR. Again, in the spirit of the same sort of idea, I want to sort of like condition my MAR to be able to push this in the next clock cycle into its proper destination. So I'm going to take now MAR and I'm going to say this. IR 3 through 15. I'm doing both these at the same time. I'll tell a couple of things about this because I think questions always come up when I actually do this in class. But let me just do this. Okay. And now I've done all these things. I want to do the, by the way, I have to do a read equals 1 here. Okay, and then here, let me just finish this up here. I'm going to just put an arrow here. This is the next side, the other side, okay? And I now will do a write. So how do I do the write? I say MEM. MAR equals MDR. And then write equals 1. So this completes the load instruction. You can call this point E. Okay. This completes, well, this doesn't complete, but it kind of initiates the completion process. So what I'm going to do now, I'm going to take E back to the very beginning. This initiates the completion of the load instruction. Load instruction. Now, where that goes back? Once I'm done with an instruction, what do? I go back to the very beginning. Maybe that's why I should not call this A. I remember. So I will call this point. I'll give it a name. Let's call this, the very end point, Z. Okay. So this E is actually like Z. Take it back there. This is the loop that's been completed. Now, which else goes to Z? This point also goes to Z. This point also goes to Z. Okay, they all go to Z. Once the instruction has been executed, it's been completed, we go back to Z. Now you notice what happens. Let's actually track this one, and then we can call it a class today. I guess so. Let's say I'm here where that dot is, like there. And what did I do here? What did I do actually? What did I initiate here? I said, hey, copy MDR into MAR. What do I need for this to happen? I need 1 clock cycle, correct? Where's that clock cycle? It's in here. Clock cycle. So when I connect that last place, D into Z, I have exactly 1 flip-flop in front of me that's going to complete this computation, which is to copy or write back into the memory whatever I want to push back into that address that I condition. That 1 clock cycle I need is created. That's why I didn't do anything in here. Like I didn't do anything in there, but I actually started to do things here because I knew that I need that extra clock cycle in order to be able to wrap my computation at the very end. Okay, so this looping is completed by making sure that each of these points, like E here, and I didn't name these things, but you can give them names if you want. The add command, the complement command arrows, they also sort of like go back to that same place Z. So that in these two cases, we have to push something into A that needs a clock cycle. That clock cycle that's needed is again created by this transition here. All right, I think it's 145, but it's actually 46 almost. 45 here, 45 there. I mean, there's only so much time I can tell you things about during which, so I think we have come to the end of another class. But we covered quite a bit. I think, doing this in slow motion, still like showing you one PowerPoint, maybe slide or two, kind of makes you, when you draw things, you kind of understand them a little better. The first time. Next time, you don't have to do any of this stuff. Now you understand this. First part of it is to understand. I think, doing it in slow motion helps that way. So I hope that you grab the most critical steps. There are only 4 or 5 instructions left: move, jump, easy, JPS. So when I come back on Thursday, I'm going to get, the move is a little bit more involved. We have 1 more indirection. I'll show you how to do that. It's going to take a couple of more, flip-flops to do. Like we were able to get the Spanish with 1 flip-flop added. That one actually will require more than 1. And then the jump, JEZ, JPS, and alt instructions are really straightforward, and we can just zap through those very quickly. And that means that when I come back on Thursday, I'm going to be able to use my VESP 1.0 code. And I also encourage you to actually bring it up on your computer. Xiaoming will be able to help you with the, how to use that technology. I'm not really going to spend much time on how to use it, or whether you have a Testudo connection or some other, I mean, every semester I know that when I try to transition to that, students have problems connecting because not everybody, but maybe maybe 10%, sometimes maybe 5%. They have a problem of finding the right utility to get to that resource. And I suggest to students, in the worst case, you can simply bring up your WAM account or Testudo account and simply say, G++, and then write the main.c that you will copy from there, and then let that run. Because you have other, means, you have other modems and other things. I don't want to get into the specifics of what resources you have and how you want it to connect to your computer. A lot of people use Macs and PCs, and on Macs, this thing runs on Eclipse, runs on Xcode. Anything that just C code, compiling will work. But I'm not going to concern myself with the hands-on part of that. I'm going to defer that to Xiaomin, hopefully it'll get you, in the right direction, and you start running small programs, because that hurdle, because it's a hands-on class, this one is, sometimes, that sort of like slows students down. So don't hold back, ask Xiaomin, questions that you have, how to connect, how to make things happen. Your particular Xcode may not work, because you have not, set its options, parameters the right way. It could be, on a legacy sort of piece of software that may be running, and you may need 64 bits as opposed. There are lots of details out there. I don't want to concern myself with those. I will focus on the main subject here, and I'll actually demonstrate, the code myself on my computer, and then we'll get to see some nice things happen. We're learning about a computer here, organization of a computer, and that's a very simple computer. It's going to get a lot more complicated. We're going to use this code mill or code appeal, which has, if you actually take all the individual cases, maybe close to like 500-600 instructions. Well, we're not going to design that machine. Don't worry about it. We're not going to go through flip-flops like this in that case. We will use it for another purpose, to understand assembly, disassembly, machine coding at a higher level, how you translate things between those things. Lots of other things will come into the class. This class is stacked with sort of like information. So you're going to have to transition from one to the next, to the next, to the next, because we're going to look at a lot of the layers of these computers. Okay, everybody, just stay, buckle up and stay, like with the class. Don't give up. It is just way too early. I know that at the end of the semester, and when I look at the class roster and the Excel sheet, at the very bottom, there are some maybe 2 or 3 students somehow who lost hope because something happened. And I feel very sorry for those students. Like don't be one of those students. And sometimes you will be one because, something bad happens in your family or something, but I understand those things. But otherwise, stay with the course. Right at the beginning, I'm just telling you this because I don't want anybody to be in that situation. Okay, try not to end up in that place, and then everything will be great. Most everybody basically walks through this class because they're committed to it. Okay, all right. Well, I just said all I have to say today. I guess I just got my message out to you guys and ladies, and I'll see you on Thursday. All right, take it easy. Be careful. I have not been
Professor,
vaccinated yet. Yes, sir.
are there any homeworks in the coming weeks or the coming days?
Maybe as early as Thursday. I'll
Okay.
send the first homework assignment.
Awesome.
Okay. Thank you so much. Take it easy. Okay.
All right.
I'll see you guys. Bye bye.
Thank you, Professor.
Yeah.
Do you mind going over the flag exceptions?
The flags. Okay. All right. Give me 1 second. And the flags here. But yeah, we haven't actually touched on flags yet. But we'll just use those flags when we get to the jump instructions, the conditional jumps. But these are basically generated, as you notice that the arrow goes from the ALU towards the controller. We're designing the inside of the controller now, not so much the data path. And your question?
So basically, whatever we did today with the flip-flops and the decoder, it was all inside A. And data path.
Yeah. So all these bits, the 4 bits, they pertain to the A register, not to the B register.
So we haven't talked about B yet.
No, B and A will be added together to come up with the sum of the 2. But the result goes into A. B is what we call a co-accumulator, which is actually used in the addition instruction and no other instruction.
We haven't talked about it today yet, right?
We haven't said anything specific about B because I don't think there's much to say about it, except that it's actually co-accumulated that gets added to A when we have to do an add instruction. For example, when we do a complement, B doesn't participate. When we do a load, B may be participating because we want to load something into B so we can add it to A, or we want to move something into B. B will be used frequently, but B is not really our focus. A is our focus. This is what's called an accumulator machine. We want to accumulate things into A. B is just an auxiliary. It's there to help us with, whatever computation we desire.
Okay.
We're not pushing anything into B. Now, when I assign you homework, I'll probably make that so that you may just use B as a target as well. Here, B is a source, not a destination. Everything goes into A, not into B, not at all. But in a different architecture, B can also be used. In fact, we have what we call general purpose registers, GPRs, or scratch pad registers, SPRs. And those things are general, so you can actually, like in the case of, for example, code appeal, we have a whole bunch of them. I don't know. Let's see if I can actually share my screen here quickly. And then I can show you this. I have to share again. Where's my share? Let me just share my screen. Okay, so if I share my screen, I can show you that, in a more powerful machine like this thing that we're going to just debate a little bit and learn about a little bit, there's a ton of registers here, not just A. I mean, look at that. We have all of a sudden 1, 2, 3, 4 registers. I can actually push it up quite a bit. All right, I can give it, like as much as 256 registers. Now, all of a sudden, did I do that? I think I might not have done it.
Do we have to download this?
Say it again.
Do we have to download this app?
No, not yet, not yet. You haven't actually done this, but you can add more registers to this. And I just changed I'm sorry, I just changed the number of bits, not the number of registers itself. Wait a minute, what did I do here? It seems like something didn't change, so I have to figure this out. But anyway, you can increase the bit width, and you can do other things with this. And I think this selection is just like not working well right now. Yeah, it seems something has to be fixed. I'm going to direct you to the code mill edition of this, because that's something that has been tested. It kind of works. Something has to be done here as far as the register updates are concerned. That hasn't happened yet. But yeah, we'll get through this sort of architecture. There's as I showed you in the first class, there's a virtual computer laboratory where I think there is an addition of this. We're still working on this technology. We're making some changes here and there. I think those changes affect sometimes, what comes up on the screen. You will have a version of this, which is called Code Mill, that you will be able to download. In fact, you can either execute it right on the screen there in the virtual lab. You have to get that Citrix. I'll talk about all these things when we actually transition to this technology, or the equivalent technology, which is called Code Mill. Okay?
Okay.
All right. Thank you for your questions. Any other questions? Anybody?
Professor, regarding office hours, if we have any questions, should we send you an email to schedule an appointment?
Yes, I think that'd be the best way to actually, and of course, like you have discussion sections. You should go to those discussion sections. Any questions are welcome. I'd be happy to, answer those questions by email anytime. Setting up some time, outside of class, we could do it, but I think it has to be, you have to really have a good reason to have that. I think the class is organized. It's a large class, as you know. They're organized basically to have discussion section and a lecture section. And, I do respond to email a lot easier than having to find myself some spare time to interact on a one-to-one basis. So email your questions. You will always get an answer. All right, everybody?
Thank you.
All right, you're welcome. And I'll see you guys on Thursday.
Thank you, Professor. See ya.
See you, Victor. Take care. Bye-bye.
Oh, hey, you're still here?
I'm here, Shane. How are you?
I don't know if you have any more time, but I was wondering about the thing you did in lecture. I was a little distracted, like installing stuff like that. You said you would load the PC, the program counter.
Are we talking about something specific, like on the diagrams here?
Yes, I think so. You would load the program counter and the MAR, the memory address register, and you said it would save a clock cycle.
Give me a second. I just have to get out of here. Every time I guess I do this. Give me 1 second. All right, 1 second. There we go. All right, so you were asking about something here. Hold on. Okay, so where's the question again?
You would load the
Up here?
PC into MAR,
Yeah,
and it would save a clock cycle with what you were doing there.
right there, yeah. Mhm.
And I was wondering if you could like quickly re-explain that.
Yeah, this one right there, yeah. In fact, this one there.
Yes.
So you can see that if I didn't do it there, like where, I say B, the MAR equals PC, right? You see that right? Like there?
Yes.
Okay, so that, saves me a clock cycle. I could have waited until I get to C to do it, but then I had to wait for a clock cycle for that to happen. In other words, I could have put another flip-flop right here. I guess you see that, you see this cursor? No, you don't. You don't, right? No.
Yes.
You see the cursor moving?
Yep.
Okay. So I could have just taken this output right there. I could have taken this and I could have sort of basically thrown a flip-flop right there to do this step. Right? Because by this time I know that I'm going to do load instruction and I happen to be here. So the two together come together. And now I know that I have to do a load. So at that point in time, I could have actually moved PC into MAR. That means I should have thrown a flip-flop in there, right?
Right.
But that would have been one extra flip-flop. If I transitioned this way, I would have seen one more flip-flop in front of me. That will slow the load instruction by a clock cycle. Is that true?
Yes.
But I don't want to do that. So because of that, I actually move this into here so that by the time I get here, whether I do an add or a complement or a load or anything else, I actually condition my piece MAR so that by the time I hit C, I have the PC in MAR. And that doesn't interfere with any of these instructions. So I gain that clock cycle, which I would have lost otherwise. I don't have a flip-flop here anymore.
It's like what's the word? Like simultaneous, concurrent. It's like concurrent.
Well, I mean, on this path that you see, there would have been a flip-flop, extra flip-flop. I just avoided that by moving this a step earlier. In other words, this operation, having no interference with any of these things, can be done here as opposed to wait until to figure out that you have a load instruction and then get up here to the point D and now throw a flip-flop in there. And now just do this MAR equals PC here. If you had waited for that long, you would have lost the clock cycle. You would have had an extra clock cycle. That's doing it here avoids having to put a flip-flop. Does that make sense?
Yes, I think I'm getting it. Also, is it possible if you can upload some of these diagrams that you draw, if you have not?
Yeah, I can. I guess I can technically do that. How do I do it? I share them, I guess. Yeah, I told the class that I'll actually put these on Elms. Yeah, I think I can do that. Yeah, I should probably do it. Because these probably are helpful to you guys. I think, there are lots of editions of this. You probably know that, I talk about this ad infinitum in my video classes on that, 2019 fall lecture series, right? Correct? Have you watched those at all, Shane?
Not yet.
Have you looked at one of those?
Hold on. Look for that real quick here. It's in files, and it's
What do you mean files?
you said
No. Yeah, these would be files. Yeah, they will be in files. I think 2017 will probably have all my lectures and stuff. What I'm saying is, the thing I was talking about was like the video lectures.
right, I see it in 2017. That's
There's
yes.
a bunch of files in there, but
Yeah, I didn't dig through everything.
Yeah, it'll
work on the
take time.
folders.
I understand. I certainly understand. It will take time for you to. But what I was suggesting that you do is actually look at my video lectures. You know, and these video lectures are there, by the way. You know this, right? And I know why you asked for this. I think, you know, you want to put it down somewhere in front of you, and you can actually just like, as opposed to watching something and not being able to interfere with it or interact with it rather.
Yes.
You want to be basically have this, you know, on a piece of paper, whatever, and then you want to mark it and you want to question it. I understand. So I'll put these on the web, and it's on Elms, that is, okay? I'll get these you know, on Elms as soon as I can. Maybe, you know, by weekend you'll have this, you know, and I think it may be best that I save. I wait until the Thursday class, at the end of which I'll put 4 classes. I guess we'll have completed 4 classes, so I can upload these every 2 weeks.
Right. All
Okay.
right. Well, thanks. And I'm gonna dig through more of these files here.
Yeah, you should. I think, you know, hopefully they'll be beneficial to you. But the critical thing is stay with the class, okay? And, you know, just try to question these things that I draw, ask questions and do things, you know, and then put your own hands on these things, you know, because this is a class that, you know, both of our programs, EE and computer engineering majors are required to take. It's a critical class for everybody.
Right. Of course.
All right. Well, I'll see you on Thursday.
Yep. See you.
Take care.